This is the first video on section 7.2 Fubini's theorem. As promised in the previous video, we have easier ways to calculate a double integral than going back to the definition of integral. And that easier way is Fubini's theorem. So if we're going to integrate over a rectangle, so that rectangle is that AB cross CD that I drew in the previous video. So we have this rectangle. And so we're integrating over R, that region or that rectangle, fxy dA. What I didn't mention in the last video is when we integrated a function of one variable, we have dx, because that represented that small part of a line segment. But in a function of two variables, we have a dA, because that represents that small little area. So that's why we have an A instead of an X there. So we have a dA for area. So we're integrating over that rectangle. And we can do that in one of two ways. So here we're looking at this double integral. And here we integrate from A to B f of xy dx. That means when we do this, we're going to regard y as a constant. Just like when we take a partial derivative. When you take a partial derivative with respect to x, we pretend y is a constant. Now we're going to find an antiderivative with respect to x, and we're going to pretend y is a constant. After we do that, we'll substitute our values for a and b, we'll subtract, that's a definite integral, and when we're done with that step, we'll have a function in terms of y. And then we'll integrate from c to d, our function of y. Or we could do it in the opposite order. We could integrate with respect to y first, but notice we have to use the y endpoints here, and then we integrate with respect to x, and we use the x endpoint second. So we go from the inside out. So here are the a endpoint, here are the x endpoints. We integrate with respect to dx first. Here are the y endpoints, but then we integrate with respect to y first. So let's look at example 200. We have the rectangle 0, 2 cross 0, 4. We're going to integrate the function 3x squared y plus xy over that region. So the way I've set this up, I've put the x rectangle on the inside and the y rectangle on the outside. You can do it the other way if you like. And so first we'll find an antiderivative with respect to x. Remember, when we do this first integral, we're going to integrate with respect to x. We're just going to pretend y is a constant. And so we find an antiderivative. So we're going to have x cubed y plus 1/2 x squared y. That's our antiderivative. Our x limits of integration are 0 to 2. So we're going to substitute 2, substitute 0, subtract. So we substitute 2 for x. So we're going to have 8y plus 2y when we substitute 2. When we substitute 0 for x, we have just 0, so we subtract. We simplify this and we have 10y. So now we integrate from 0 to 4 of 10y dy. This is simply a Calc 1 problem. Find an antiderivative, 5y squared, limits of integration 0 to 4. Substitute 4, substitute 0, subtract, and we have 80.